Hello, we're Team Soft Robotic Hand from Worcester Polytechnic Institute. My name is John Morrow, and presenting with me are Jacob Torrey, Riley Larkins, and Stephen Dang. Our advisors for this project are Professor Dimitri Berenson and Calder Phillips Graflin. Our team designed a robotic hand featuring soft pneumatic actuators as fingers. These fingers incorporate sensing for closed-loop control and are deformable, which enables them to perform grasps on objects with reduced planning. Furthermore, this hand is designed to easily integrate with other robotic systems. In this presentation, we will review the problem we solved and the requirements our solution had to fulfill. We will then cover our system design, how the design was measured against the requirements, and what makes our solution not just unique, but on the leading edge of robotics research. Finally, we will discuss how we managed our project, including risk management and budgeting, and goals for future work on the project. We feel that there are two unsolved problems that are keeping robots from widespread usage and integration into our society. First, there is a significant trade-off between precision and cost in robots. Increasing precision in both actuation of the robot and in its sensor's perception of the environment can significantly increase costs. This problem makes affordable robotic systems difficult to use effectively. In addition, traditional grippers have issues grasping fragile or irregularly shaped objects. As the complexity of the object increases, the difficulty in planning and grasp execution grows quickly. In the DARPA Robotics Challenge, robots that represented the current state of the art in the field were given 15 minutes to simply open a door or turn a handle. Our goal was to design an end effector system which would augment existing robotic systems to minimize these problems in a variety of tasks. This would allow cheaper, imprecise systems to be utilized in a wider range of tasks, replacing more expensive systems, or being used for tasks previously difficult to automate. Before we started anything, we came up with example use cases which we would use to develop our project needs. At Frito-Lay's, human workers pack potato chip bags into boxes instead of an automated system. In this situation, a robotic system would have to handle the bags without popping them. In our second use case, if a robot were to pick fruit from a tree on a farm, the end effector used needs to handle the fruit so it does not damage it. We developed 6 needs based off of these use cases. First, the end effector has to be able to respond to the environment with an appropriate reaction time. It also has to be versatile enough to handle a wide range of objects on its own. The end effector also has to be able to withstand the environment that it will work in. To increase the effectiveness of the cheaper robotic systems the end effector will be a part of, it must improve upon the uncertainty present in the system. Also, if we want robots to interact with people, the end effector should have an inherently safe design. Oftentimes, active systems could be outsmarted or manipulated to fail by the humans they are trying to protect. Finally, the end effector system has to be of low enough cost to justify buying it as an add-on to an already expensive system.
To fulfill these needs, we created a hand that utilizes soft pneumatic actuator fingers to tolerate imprecision and be inherently safe. Each of the fingers is instrumented using embedded e-gain sensors to enable closed-loop control of both force and position. Articulation of the joints allows the hand to be reconfigured when necessary to grasp irregularly shaped and deformable objects. These design choices resulted in a system that meets the requirements that we set. Our final system costs $860 in parts and materials, which lies within the price range of the commercially available alternatives. Testing has shown that the initial prototype fingers could withstand 7 months of use. Reconfigurability and deformability of the fingers enables the hand to adapt to many different objects and environments. The embedded sensing further increases the adaptability of the hand and allows grasping of delicate objects. An overview of the system is shown here, and will now cover the different subsystems in greater detail. The highest level of controls are handled by an Intel Atom. It is responsible for calibration, user input, and grasp analysis. All of this is built on ROS, making it extensible and allowing easy integration of additional systems and interfaces. The Intel Atom is connected to an Mbed FRDM K64F, which runs the embedded control systems. On the K64F, a custom shield handles the connections between the microcontroller and the motors, solenoids, and finger sensors. Finger articulation is controlled by the K64F and measured using quadrature encoders. Finger actuation is controlled by a set of solenoid valves that are supplied pressure from an external compressor. Sensing of the fingers is handled by custom boards built around ARM Cortex M0s. These boards perform the signal conditioning and reading of the sensors embedded in the fingers and report results to the K64F. To quantify the hand's grasping abilities, we used the set of items used by the Amazon Pick Challenge. This set of items represents a wide variety of shapes, sizes, and materials. To measure our success against these items, we used a pre-planned path to approach and attempt to grasp an item at a known location. The grasp was then tested by shaking the item with a repeatable path. The percentage of successful grasps was recorded for each item. We show a comparison between the success rate of the hand without fingernails and with the most successful set of fingernails to illustrate the progress that was made and the importance of a rigorous evaluation process. The controller was evaluated by observing steady-state error, response times, and overshoot when different set points were commanded. The controllers were tested with both step inputs of various sizes and ramp inputs. To test the force controllers, an obstacle was fixed at various positions in the path of the finger, and then the applied force of the finger was controlled. The maximum force position controller commanded different positions while the obstacle was still in place. When positions beyond the obstacle were commanded, the force output of the finger is limited. The control law guarantees that fingers will not apply more force than a given threshold, while still being able to command different positions when the force is below the threshold. In order to meet our functionality requirements, there were two main areas that required significant innovation: the control of the fingers and the physical design of the fingers. Previous work in the field of soft robotics has explored open-loop control of the fingers. However, for our needs, we needed finer control. By utilizing embedded e-gain sensors developed at Carnegie Mellon University, we were able to implement control of the fingers beyond any work previously done in the field. The e-gain sensors utilize eutectic gallium indium as a conductive fluid within microchannels in the finger. As the finger actuates, the sensor stretches, changing the cross-sectional area of the channels in a way similar to how strain gauges function. This change is then detected as an increase in resistance and measured by the circuits on the fingerboards. In our testing, we quickly discovered that one area in which conventional SPAs perform poorly is grasping objects off of flat surfaces. To solve this, we drew inspiration from human fingernails, which are used to pick up items from smooth, flat surfaces. By incorporating these rigid elements in our otherwise deformable actuators, we were able to significantly improve the rate at which items could be grasped from a flat surface.
No matter the experience and skill that an engineering team has, a project must be well ran to be successful. Throughout this project, we constantly strove not only to engineer a solution to our problem, but also to effectively manage ourselves as a team. The first challenge was determining team composition and responsibilities. With our solution requiring skills from multiple disciplines, our choice of teammates was crucial to our success. In the end, we formed a team with strong experience in embedded controls, electrical design, soft robotics, mechanical design, and system engineering. Conversely, time management and setting deadlines has been a point where we have struggled since the beginning. Without the experience necessary to accurately estimate the time required to complete the set task, the schedule we set in the beginning of the year was impossible to follow. During the course of the project, the team dealt with several risks between the design and execution phases. When acquiring parts, hardware lead times and hardware availability often became an issue. Also, at the beginning of the project, the success of certain subsystems, namely the precision control of the fingers and the performance boost provided by the fingernails, was unknown. To mitigate these unknowns, we adjusted our project timeline appropriately. Prioritizing uncertain tasks like the controllers allowed us for more development time, and other deterministic tasks were worked into the schedule later as a team member finished their higher priority task. When planning, it was in our intent to allow enough time for testing and fabrication. With minimal funding available before advancing to the finals, we took great care when selecting and purchasing components and materials. While difficult, this worked in our favor, as one of our requirements was to keep the overall cost of the hand to a minimum. By far, the largest item on our bill of materials is the Intel Atom. While a significant cost, it is the component that enables everything beyond the most basic functionality. In the production of not just a usable hand but an intelligent system, this extra functionality is key. When looking at the development cost, a notable expense was silicone for the series of finger designs. As an important component of the system, a significant portion of time was spent revising and refining the finger design. While the cost to produce such a large quantity of fingers was non-trivial, the benefit of the efficacy of the hand was significant. Now looking ahead, there are several things that we would like to change. First, we would like to add force sensation to the palm. This addition would contribute to a better understanding of the quality of grasp in the system. Next, we would like to refine the fingernails to be able to grasp all the test objects successfully. Likewise, the finger construction process should be refined to remove the high chances of construction defects in the mostly handmade process. Finally, as a stretch goal, we would like to add grasping analysis so the hand could determine the quality of grasp without human intervention. We would like to take this time to thank the Intel Cornell Cup for giving us the opportunity to participate in this competition and for their support of our project, the Soft Robotics and Bionics Lab at Carnegie Mellon for their help and expertise in the field of soft sensing, and to Advanced Circuits for their sponsorship of our printed circuit boards. We would also like to thank our advisor, Professor Dimitri Berenson, for his help, experience, and support, Calder Phillips Grappling for his technical experience, which he was willing to share with us at all hours of the day, and to Joseph St. Germain for his advice in helping with manufacturing. Thank you for watching.